Okay, so here I'm talking about the remainder of the presentation. Here I'm talking about windowing. Now, windowing is basically used to give a good frequency response, and the choice of window that I'm using here is a Hamming window. So after doing pre-emphasis on the speech signal, the frames are divided into 10 milliseconds, and each of this frame is then multiplied with a fixed length window in time domain. So there's an equation is also given for windowing where h of n is equals to 0.54 minus 0.46 multiplied by cos 2 pi n by n naught. Now the value of n ranges from 0 to n naught, and h of n is equals to 0 otherwise. So the figure on the left shows the Hamming window used, and the figure on the right shows the windowed version of the speech signal black. Now in the previous section we can see the emphasized version of the speech signal, and in this we see the windowed version of the speech signal black. Next, we are talking about fast Fourier transform. So here the main concept is to perform a discrete Fourier transform on the data signal. Now this helps us in basically converting the data from a time domain sample to a frequency domain sample. Now the number of operations, like to reduce like to now DFT takes a lot more operations. So what we are doing is using FFT, that is like fast Fourier transform. Now fast Fourier transform helps us in reducing the number of required operations from like n square operations for DFT to n log n operations for FFT. Now the equation for calculating FFT is also given there. Now in this model what we do is we calculate a 64 point FFT, taking each windowed speech frame, and the waveform for the 64 point FFT is given here for the signal black. Now next, we are looking at the Mel scale and the Mel filter bank. Now, Mel scale is nothing but a perceptual scale of pitches. Now, in Mel scale, we always consider that the receivers are always equidistant from each other. Now, Mel scale helps us in doing our calculations and doing the feature extraction, and it helps us in matching the words also. So what we are doing is like I'm showing you the equation here, which converts like the normal frequency range from hertz to the Mel scale, and the next equation just does the opposite of that. It converts the Mel frequency range to normal frequency range, and the range of frequency that I'm using here is 0 to 4 thousand hertz. So the plot here below is shown. It's a comparison between the Mel frequency and the normal frequency in hertz, where normal frequency is taken in the x-axis and the Mel frequency is taken in the y-axis. Next here we're continuing about the section for the Mel scale and the Mel filter bank, but now the Mel filter bank is created using the Mel frequencies. So the Mel frequencies have been obtained using the previous equations here. That is like m is equals to 2595 log of base 10 of f by 700 plus 1, which is equals to 1127 log of f by 700 plus 1 to the base e. So now this equation helps us in actually calculating the Mel frequencies, and the following equation basically defines the Mel filter bank. Now this the value of small m, it ranges from 1 to m. Now the capital M is basically defines the maximum number of filters what we can use. Now for my model, I'm using 30 filters. So the data for like all of these are taken and it is stored, and this is called a Mel filter bank. And the figure on the bottom is for a Mel filter bank in an image form. Now here the squares represent a non-zero value, and where there's no square it represents a zero value, I guess. So and the this is a colored figure of like showing a mail filter bank in an image form. Next, I'm going to talk about the feature extraction that is done on the speech signal. Now, in feature extraction, what we do is we do this. It's called a Mel frequency substral coefficient. So, which is in short MFCC. Now, MFCC is basically done to measure the acoustic features of the speech signal in the substral domain. Now, to do this, we need a set of nonlinear filters, and MFCC can be calculated for every frame by like moving each FFT coefficient through a MEL filter bank frame by frame. Now, size of frame is taken as 10 milliseconds, and an overlap frame size will be like 5 milliseconds. Now, the coefficients for the MFCC are taken from the color map, and here we can see the MFCC for the speech signal black. So if we go back, we had done our fast Fourier transform and the windowing and the pre-emphasis, and now we're doing the MFCC on the speech signal black. So for every word that we'll be speaking, we'll be doing this feature extraction, because this will help us in analyzing what speech has been spoken, and that will be detected against a set of vocabularies. So over here is the plot is just shown for the word black, and the maximum number of like MFCC coefficient that could be extracted is in the range of 10 to 13, and for my model I'm using 13 MFCC coefficients. Now next I'm talking about pattern matching. In pattern matching, the concept used for matching the vectors is Euclidean distance approach. Now the extraction of like feature vectors like MFCC is done, and the speech pattern now only differs in the substral domain. To distinguish between every word that we say, uh, we measure the Euclidean distance, and the equation for that is given here, whereas where z is the substral distance. Now the thing is, the word with the with the lowest substral distance is the correct word. In this set of examples I've shown you in the first set, where the input word is black, and we can see that the distance, the substral distance, is the lowest for the word black. So that means the word black is correctly detected. Now, in the next set also we see we're doing a word in brown, and we can see that it's also correctly detected. But in the next figure we see we're doing black, but we can see that it is not correctly detected, as the substral distance for the word red is lower than the word black. So that means that we have an error. So the model that I have designed till now is only helpful in providing an efficiency for about a range of 50 to 95%. But this efficiency completely depends on the environment the data is recorded in, and it also depends on the size of the vocabulary database. Now, from my calculations, I can predict that if we increase the size of the record of the vocabulary database, then the efficiency for this model will increase. Because the main compromise that I have done here is on the size of the vocabulary database. So if that is removed, then this will have a very high efficiency of around 95%. All right, so moving on to the next section, here I'm discussing about how the recognition software can be implemented for getting for doing for different applications of cellular communication actually. So first we look at the capability of the recognition software. So it can do like three types of recognition. First is a single word recognition. In single word recognition, it's just the speech consists of only one word. It is spoken, and then it is like the acoustic vectors are defined for this word, and it's matched against against the system vocabulary. And if there's a match, we do as like what was a command. For example, say we can try say reservations to book a ticket. Now, if the user says reservations is taken and matched in the system, and if there is a reservation, the command is proper and forwarded, or else like the user will be asked to like tell the command again. So this basically recognizes only a single word, and the effort has been taken to make this speaker dependent or independent. It could be anything, so it doesn't depend on any particular language or anything. As long as everything is supported in the system vocabulary, the recognition software works perfectly. Now, next is concatenated word recognition. It's just same as single word recognition, but here we are like showing you multiple words together. So the thing is like each and every word is taken separately and then is similarly analyzed and is again matched with the system vocabulary to provide the proper results. So here also it's just the same thing has been done. Next is complete speech recognition. Now this complete speech recognition basically incorporates everything of the above two models. This is mainly used for taking dictation or for communicating with an automated system. Now, this model needs to have a very large vocabulary size also for detection, otherwise it will be a problem. But the system is again again speaker dependent or independent. So these are the three kind of capabilities that the software has. Next, we'll be looking at the recognition model that for cellular communication that has been proposed. So here in this model, what we are doing is we are storing the acoustic. We are like showing you the system that could be used for detecting speech and doing a proper recognition. The software can be implemented and stored in the system and used accordingly. So we can see the acoustic vectors that will be obtained from this software model is used to analyze the speech, and the main components that will be used in this model is actually the word match and the sentence match. Now for word match, the basic thing for word match is that the sentence is broken down into different words, and each individual word is again matched to the system vocabulary. And if there is a match, the proper command is forwarded, and it's properly analyzed. But and if there is not, then we again try to match it back. So word match basically takes the whole speech and divides it into the number of words that is in, and the proper analysis is then done. Another component here important is the sentence match. This component is specifically important as it analyzes the syntax and semantic rules, and it follows that perfectly. So a speech when it's like converted. Now suppose we use this for speech to text format, so we need proper semantics, otherwise the user cannot read a particular text. So this model this sentence match module is utmost important in those cases. And the sentence match heavily follows all the syntax and semantics rules, and after the speech has passed through the sentence match module, it is then properly analyzed, and which means we will have our output that is there. Now the all the capabilities will be like is completely dependent again on the system vocabulary and the environment, but this model will be able to do all the will be able to implement all the capabilities of the recognition software, and this model can be used for various applications of cellular communication ranging from anything that we can think of, and therefore the recognition software can be exploited in our model and be exploited using this model. Now next section I'll be talking about the performance, but that is again in the third video.